We're learning about autoregressive order 1 processes, and we kind of saw autoregressive order 2 already. And I just want to mention that there's kind of two ways you can go with this. You can go the statistics route of saying, I have an interesting data set. I want to see if I can model it with AR1 or AR2 or something like that. And that can make for a great project. Another way we can use the whole autoregressive order 1 concept or order 2 is sometimes we want to generate our own data to feed into a simulation. Maybe we are simulating demand for an emergency room, and demand this hour might have some relationship to the demand last hour if the roads are icy, for example. So even after accounting for temperature, we might still have autocorrelation from one hour to the next, and we might want to generate a lot of simulated data in a realistic way, so we'd need to use an AR1 or AR2 process or something to do that. So let's play with generating data from an AR1 model, and that can also tell us about some of the statistics that are going on in AR1 models. So let's start by just trying to recall the formula for an AR1 process. You could call it your own little pop quiz. So pause the video while you try to write it down for yourself. Okay, welcome back from pausing. So it is yt equals a1 times y of t minus 1 plus some ID noise. So to simulate that, what parameters do we need to say, give a definite value to, so we can do some computations? So take a sec to think about what we need to specify in order to simulate this process. Well, we've got A1 here. That could be different for different models, so we'll save a spot for A1. We said the noise, we expect to have a mean of 0 with some standard deviation, usually not a standard deviation of 1. So we'll say we'll have a standard deviation. And then a perhaps surprising thing is we need to say what we start at. If I'm going to predict y1, I need to know what y0 was. You don't have to start at time 0, but it's quite common to start at time 0. So let's just put in like 0.65 here. Standard deviation, we can put in anything we want. How about 7.3, just to prove that it doesn't have to be any particular special number. And y0, let's put in, how about 13? 13 is a perfectly good kind of arbitrary looking number. So we'll put yt at time 0. We'll just make that a copy of y0 here. And now how do I fill in a formula for y1 based on y0? So try to fill that in yourself before watching me do it. Okay, welcome back from pausing. So we'll say my new value is my A1 value, and lock that with an absolute reference, times my previous Y value, plus the noise, which I want to have a standard deviation of 13. So I can do this 13, lock that reference, times, I've got a normal distribution, standard normal 0, mean 0, variance 1. And then I can fill that down. And I've got some of my old analysis methods here. Let's just go and investigate this normal noise. So I've got a uniform random between 0 and 1, and then I'm using the normal standard inverse function. Again, this isn't the best way to generate it in industrial situations, but it's good enough for classroom situations in Excel. And same formula there. So I've got my y of t and my next y of t. These are only showing 2 decimal digits, but really they've got more digits than that. And down near the bottom, remember our next and our next have blank cells where we don't have any next or next data. So let's take a look at what we're getting in the autocorrelation function. Our autocorrelation at lag 1 is 0.65, which is pretty much what we put in there. Let's check and generate new random numbers by pressing F9 on a Windows machine or Command T, Command equals on a Mac. We see we aren't always getting 0.65 here, but it's plausibly equal to 0.65 on average. What if we change this to something like about 0.37? Are we getting something like 0.37 here? Well, haven't seen a value. Okay, there's below 0.37. So it's kind of plausibly equal to A1 like we said it would be. And let's take a look at the autocorrelation function graph. It's actually okay to use a negative value for A1. How about negative 0.9? And let's take a look at the data set itself. Actually, here's the data set itself. Let's move that up and see as we change the A1 coefficient. So this is negative 0.9. Would you say that that's bopping back and forth above and below the axis? Whereas if I use positive 0.9, then it tends to stay above the axis for a while and then below the axis for a while. We could try 1.1, see what happens. And we get apparently exponential growth to the negative. Or if I hit F9 again, sometimes it grows exponentially positive, sometimes exponentially negative. But if we hit negative 1.1, then we see alternating sign exponential growth. So that's kind of interesting, but probably don't want your values getting up to 10 to the 15th or whatever. So we usually need A1 to be between +1 and -1. Let's put in 0.9, for example. So let's think more about the values we're seeing for the autocorrelation function. We said for an AR1, whatever we put in for A1 is the autocorrelation we see at lag 1. What are we seeing at lag 2? We're seeing 0.84 here, and we can see a few examples of that. Here's the interesting thing. Our model doesn't have any obvious dependence at lag 2. It's not like there's a y of t minus 2 in our model, so we might kind of expect the autocorrelation at lag 2 to be 0, because we aren't saying today depends on 2 days ago directly. But in our model, today depends on yesterday, which depends on the day before, so you could expect some correlation to kind of carry through in the meantime. And that's actually what's happening here. So what we can say is, in theory, for an infinite data set, the ACF at lag 1 is A sub 1. This is for an AR1 model. So I'm not saying we're ignoring noise, but we're saying if the data is so big that the noise all gets averaged down to be not really affecting the numbers, this is what we'll see. So an ACF at lag 2 is actually A1 squared. It's like you're applying A1 to 2 days ago and then applying it to yesterday. So it kind of makes sense that we would square that. And then the ACF at lag 3 is A1 cubed, etc. So that is exponential decay in the ACF values. So that's the ACF for an AR1 model. ACF for an AR2 model is much more complicated and pretty interesting, and we'll have to just let you read about that in textbooks. So the lesson here is, just because you see a non-zero correlation at lag 2 doesn't mean that an AR1 model isn't appropriate for your data. What you could ask yourself in a very kind of heuristic way is the ACF at lag 2 roughly the square of what it was at lag 1? Let's try to get back here. So we know that 0.9 squared is 0.81, and here we're seeing values that are kind of plausibly 0.81. Well, let's type that out. Just because you see a non-zero ACF at lag 2 doesn't mean that an AR1 model is a bad fit. If the ACF at lag 2 is substantially different than the square of the ACF at lag 1, then you should maybe start thinking about AR2 models. So it's good to remember here that the ACF at lag 2 is saying how correlated is today's data with 2 days ago, but it's ignoring the fact that we might have known what the intermediate value was. So it's saying how well does 2 days ago predict today, ignoring the day in the middle. But what we'd rather know usually is how much better does my prediction get if I'm already using yesterday? How much better does my prediction get if I include the day before it as well? And the answer to that is comes from the partial autocorrelation function, PACF, which is a real pain to compute in Excel. You basically need a plugin to do it in any automated kind of way, but it's built into the statistical routines in R and Python. So that will have to be its own other video.